All right. Scientists use the scientific method. So I'm sure you guys heard of science. I'm sure you guys took science classes in high school and maybe in college, but a lot of scientists really don't understand what the scientific method actually is and how it actually works. Okay, so in general, all scientific inquiry follows a standard process for trying to understand the natural world, and that's what really what science actually is. Science is a study of the natural world. Okay, uh, okay. So here's the scientific method. Okay, the scientific method has multiple interrelated parts. Okay, um, okay. So the scientific method begins with observations and questions. Okay, observations are the knowledge amassed before an experiment. Again, so you make observations, like for example, we know there's something called rotavirus. Okay, we want to design something to prevent it, and we'll create a vaccine. Okay, and so you'll ask the question: is the rotavirus vaccine effective? Okay, you consult prior knowledge. You read the previous literature on vaccine, but ultimately you have to formulate a hypothesis. A hypothesis usually goes in the form of an if-then statement. If the vaccine works, then people with the vaccine should get less ill. Okay, you need to formulate a hypothesis. Okay, for example, the vaccine will stimulate the immune system and therefore be associated with a reduced incidence of coronavirus illness. That is their hypothesis. Okay, if the vaccine works, okay, there will be less incidence of coronavirus. Okay, so here's the if-then statement. Okay, so these two are together are what makes the hypothesis. Okay. Then you have to collect the data. The data must be objective and quantifiable. It can't be subjective. You can't just say it works because I say it works. Like that doesn't work. Multiple people have to be able to look at the same data and say it works. Okay. All right. Okay. The data can either support or refute the hypothesis, and then you draw your conclusions and you make observations. And what we'll do this experiment. We'll do this in class when we meet. We'll talk about what experiments are and stuff like that. So, okay. After all that's done, the research is actually subject to peer review. So what peer review is you send your results to basically your worst enemies. Okay, they're not your worst enemies. They're people who are doing similar research to you, but they are actually doing similar research to you, which is sometimes problematic because they know your experiments as well as you do, and they know what flaws are there, and they know exactly where to look. And some of them are actually doing very similar experiments and competing with you for the same grants and stuff. So it is problematic. But these people also know your data best. And what they do is they challenge you on how to do the experiment better. Why didn't you do this? Why didn't you do A? Like what, you know, this is wrong because of this. And so you go back and forth with these people a couple of times. And honestly, it's really, a really painful experience to go through. Like every time I've gotten a peer review back, I felt like killing those people who actually wrote the peer review until I actually take a day and process it. Okay. And then I realized they're probably right and I should do something differently. And then I do that and eventually it clears peer review. And I peer review articles before, and I'm sure they hate me too. So and they go through the same visceral response on their end as well. So it's not a one-way street. But ultimately, it makes its way through, and you publish the data. But that being said, because you've published, like you did the research and others who are most knowledgeable in the field have criticized you, the data, if it comes out, is most likely to be true. Okay, so an experimental plan is a careful plan, and it has to involve certain stuff. Okay, it has to involve a sample size. The sample size has to be pretty big. It depends on what type of experiment you want to do. Like for example, for my sample size in flies, it's usually several hundred. In humans, it's probably gonna be less than that, like 20, 30 people would be a good sample group. Okay. And then you have to have two variables, the independent variable and the dependent variable. Okay. The independent variable is what's being manipulated, and the dependent variable is what's being measured. Okay. For example, okay, in our case, the independent variable is the dose of vaccine. So the independent variable is a variable that the investigator manipulates to determine whether or not it influences the dependent variable. So you either get the vaccine or you don't. That is the independent variable, and that's chosen by the researcher or investigator. Okay, so the variable you decide is whether you get vaccine or not. Okay, so that the independent variable is usually the one that's decided by the investigator. The dependent variable is usually the one that's measured by the investigator, whether you get sick or not, whether you get a rotavirus or not. So that is dependent on whether you get the vaccine or not. So the dependent variable is always dependent on the independent variable. Okay, the standardized variable or control variables are things that the investigator controls. Like all the kids should be the same age. All the kids should start off with good health. All the kids should be like male or what female or like not have other diseases and stuff. Okay. The control is usually the basis for comparison. So you have an experimental group and you have a control group. The control group is usually the people who are either getting nothing or getting placebo. A placebo is a sugar pill. It's something that's lacking the active ingredient in the vaccine. Okay. So you can then graph the data. Okay. If you graph the data, you can see here, okay, in the second fed rats, they have much higher percentages of getting cancer or tumors. So for the second fed, the parrots, 19 of them that are fed saccharin get tumors, and 3% of the parrots, and the offspring, 27% have tumors, okay, as well as 0 in the offspring. Okay. Okay, so let's see if we can answer this. Okay, the dependent variable versus the independent variable. The dependent variable is the one you measure, so this is a dependent variable. Okay. All right. The last part of this is the chapter is scientific theories. Scientific theories are comprehensive explanations. Okay, so the word theory in science, okay, is very different than the word theory outside of science. When we talk about theories outside of science, we're kind of being a guess or hypothesis. Okay, in science, theories are the biggest overarching ideas in science. Evolutionary theory, germ theory, gravitational theory. Okay, all of these are really big, broad things that cover cell theory, like big, huge things. Atomic theory. Okay. theories are potentially falsifiable. So all things in science are falsifiable. You can falsify if you do the right experiment and the data actually shows that the theory is wrong. Okay, but it's actually really hard to do because scientific theories are supported. Every scientific theory is not an idea; it's a conglomerate of ideas that all fit together in a seamless network. So to try to, it's doable, but it's not likely. Okay. Okay. So scientific theory has limitations. Okay. So it has some data can have multiple interpretations. You can screw up experiments. Okay. The data, because it has to be published and go through peer review and multiple rounds, and take a long time. Okay. And it's limited existing phenomena of the natural world. Okay. So science can only answer questions about the natural world. It cannot answer questions about the supernatural world. And that's something that, some people really kind of mistaken. Like there's no way to prove that there are no fairies in the world. There's no way to prove that, an invisible monster is secretly trying to hunt you down and kill you. There's probably not true, but there's no scientific test for it. Okay. Okay. Biology continues to advance. So technology is a practical application of scientific knowledge to provide and provides tools for scientific inquiry. So technology, medication, testing for results, like testing to see if you have COVID. All of those are scientific technology. Okay, so one of the key things about technology is science really tells us what we can do with technology. It does not tell us what we should do with technology. Okay. All right, so that's it for this chapter. I'll see you for chapter 2.